So using derivative rules for inverse functions, it's fairly straightforward to show that the derivative of the arctangent is 1 over 1 plus x squared. And of course that makes the antiderivative of 1 over 1 plus x squared equal to the arctangent. That being said, I think it would be super satisfying if there was some sort of geometric interpretation of this identity. And in fact, I found just that. And I'd like to present it today. And this is from an article from the College Math Journal in 1989. Okay, so well, since we're doing a geometric interpretation of this antiderivative rule, we should probably get some sort of picture involved. And that's what I've got over here. So here I've got the xy plane, and I've graphed in this peach color the graph of y equals 1/2 times 1 over x squared plus 1. And now what we'll do over here is put a point out here. And this point out here will be along the x-axis, and it'll be the point t, 0. And I'm going to give this point a name as well. This is going to be point R. And so phrased in terms of this point and this graph, we can rephrase our goal, which is like, showing this identity via geometric means, as 1/2 times the integral from 0 to t of 1 over x squared plus 1 dx is equal to 1/2 times the inverse tangent of x. Or sorry, that should be the inverse tangent of t. So this is in essence the definite integral version of an antiderivative, where you go from some sort of fixed lower point to a variable upper point. Okay, so the left-hand side of this equation is clearly giving us the area under this curve. And so now we need to interpret the right-hand side of this equation as something on this graph. And here's how we can do that. So we'll go down here in the y-axis and we'll add another point, and that'll be the point 0, -1. And we're going to name this point as well. We'll name this point P. Okay, and now what I'd like to note is that if we make a line segment from P to R, so let's get this line segment on the board, then, well, what's this angle right here? Well, let's observe that the tangent of this angle is equal to opposite over adjacent. Oh, but notice the opposite length is t and the adjacent length is 1. So that makes this angle, which I'll call theta just on the picture, equal to the arctan of t. So I think that's pretty clear just by rules of trigonometry. So that's good. We've got this left-hand side into the picture. Now we've got this right-hand side, or maybe something similar to this right-hand side in our graph as well. Now we'd like to try to start to tie these together. And the way to do that will be to split this region above the x-axis and this region below the x-axis, each into two pieces. So let's start with this part above the x-axis. So let's put a vertical line segment here from our point T0 to the graph. And then we'll take a horizontal line segment until we intersect with the x-axis. Okay, so that's going to be over there. And of course, we can easily calculate this coordinate right here. This coordinate will be t, comma, 1/2 times 1 over t squared plus 1, because it's going to be on that graph. And now let's name this region up here A sub 1. Okay, so let's say this shaded bit up here is region A1. And then let's name this shaded little rectangle down here A2. Okay, so there, we've got our labeling A1 and A2. And now let's observe that it's really easy to calculate the area of A2 because it's a rectangle. In fact, it's a rectangle where the width is t and the height is 1/2 times t squared plus 1. Okay, so let's gather that information over here, and we'll maybe color code it a little bit. So here we've got the area of A2 is, like I said, equal to t over, I'll write this as 2t squared plus 2 because I'll just multiply it out. Okay, so now let's maybe also calculate the area of A1, but we can calculate the area of A1 via an integral. And so you might say, okay, well, we can just take the integral from 0 to t of 1/2, 1 over x squared plus 1, and then subtract off this area. But what we'll do instead is take the integral along the y-axis. So in order to do that, we need to solve this equation in terms of x. Because if we're doing an integral with respect to y, of course, we have to like invert this. Okay, so let's see how that might go. So here we've got 2y is equal to 1 over x squared plus 1. And then inverting that, we'll have x squared plus 1 is equal to 1 over 2 times y. But of course, that's going to make x squared equal to 1 over 2 times y minus 1. Or we could put some things together here and we'll have 1 minus 2y over 2y. Oh, but now we can take the square root and we'll have x equal to the square root of 1 minus 2 times y over 2y. Okay, so there we have it. Now we have this curve as a curve of x as a function of y. And now, well, we'd like to integrate that from this lower point to this upper point. So let's do that. Okay, so we've got our area of A1 is equal to, we're going to integrate that with respect to y. So that'll be the integral, the lower bound, the lower y bound, I should say, is this 1 over 2 times t squared plus 2. The upper y bound is this point right here where x is equal to 0, making y equal to 1/2. And then we're integrating this function right here, this square root of 1 minus 2 times y over 2 times y dy. Okay, so now let's perform a change of variables to simplify that a little bit. And that change of variables may seem non-obvious, but what works here is we'll set u equal to the square root of 2 times y minus 1. But now you can check that that makes du equal to dy over the square root of 2 times y. And then let's see, we can add 1 to both sides and square both sides, and we'll have u plus 1 squared equal to 2y. That's going to make 1 minus 2y, which is what shows up inside the integral, equal to 1 minus u plus 1 quantity squared. Okay, so let's maybe box this off and perform this change of variables to see what we get. So let's take care of the bounds of integration at the end, but what we'll have is the following. Notice that this dy over the square root of 2y gobbles up that denominator, and then we're left with the square root of 1 minus u plus 1 quantity squared du. But now, what about the bounds of integration? So our upper bound of integration is going to be 0, because observe we get the square root of 1 minus 1, so that's obviously equal to 0. And then throwing this into our function of u in terms of y, you'll see that our lower bound of integration will be equal to 1 over the square root of t squared plus 1 minus 1. And that's actually where we're going to stop for the area of A1. And, well, that might seem like sort of a ridiculous place to stop, but in fact, that'll be exactly what we need for our purposes. Okay, so let's collect that over here. So we've got the area of A1 is now equal to this crazy integral here. So that lower bound of integration, So that's 1 over root t squared plus 1 plus 1, or sorry, minus 1 up to 0 of, let's see, we've got square root of 1 minus, and I'm going to change this back to y's. So we've got y plus 1 squared dy, where I just do a dummy switch of variables from u back to y. Okay, so we've got our area of A1 and our area of A2. So these two areas are going to kind of obviously add up to this object right here, just based off the fact that they're partitioning all of that stuff above the x-axis. So now let's see how we can partition what's going on below the x-axis. Okay, so there we've had it. We've partitioned, well, the part below the x-axis. We're actually not going to need this little sliver up here. So let's see how I built this. So what I did is I took a circular arc where the center was at R, and the radius, or a radius, goes up here to the origin, and I arced it out until it intersected this yellow line segment. And then we take a horizontal line from this intersection point along over to the y-axis. What's above is what's called B1, and what's below is B2. Okay, so let's calculate this area of B1 first. So we're going to integrate this with respect to y as well. So notice that it'll be the area between this circle and the y-axis, between this y point right here and the origin. So let's get this equation of the circle on the board. Okay, so notice it's got a radius of 1 and it's centered at this 0, -1. So that means its equation is x squared plus y plus 1 squared equals 1. Okay, so now let's go ahead and solve that for y. Okay, so now let's go ahead and solve that for x. So that means we're going to have x equal to the square root of 1 minus y plus 1 quantity squared. And we took the positive root there, of course, because we're looking at the right-hand half of this circle. Okay, so now let's get started. So we've got our area of B1 will be the integral from something up to 0 of this object. So we've got 1 minus y plus 1 quantity squared dy. And now, well, let's figure out what this point right here is. But check it out. It's the intersection point of this circle and this line from P to R. So let's maybe get the equation of this line on the board. Well, the line has a slope of t and it has a y-intercept of -1. So this line has equation y equals t times x minus 1. So all we have to do is intersect that circle and that line. So let's see, we'll put this value of y into the equation of our circle, and that's going to give us x squared plus t times x squared equals 1. Of course, the -1 and the +1 are going to cancel. But observe that we can factor an x squared out of this, and we'll be left with 1 plus t squared, and we have that's equal to 1. Oh, but now solving for x, we'll have x equals 1 over t squared plus 1. But of course, we want the y value here. So you can easily calculate the y value by plugging this in for x right here. And we'll have y equal 1 over the square root of t squared plus 1 minus 1. Okay, so that means we can put this up here for our lower bound. So 1 over radical t squared plus 1 minus 1. And now we can collect over here the area of B1. So we have the area of B1 is represented by the integral that we have written over there. But that happens to be exactly the same as the integral that represents the area of A1. So let's just swing this equal sign up, and what we've just shown is that the area of A1 is equal to the area of B1. Okay, so now let's move on to calculating the area of B2. Okay, so now we're ready to calculate the area of B2. But observe that B2 is simply a triangle. So it's a triangle with these vertices P, C, D. I just labeled the C and the D. But since CD is parallel to the x-axis, that's going to be similar to triangle POR. So if we can find the area of triangle POR and then maybe the proportion of similarity, then we're good to go. Okay, so let's observe that the area of OPR, so triangle OPR, is equal to, well, that's easy. That's T times 1, that's base times height, over 2. So that's going to be T over 2. And then let's also get on the board that triangle OPR is similar to triangle, let's see, PCD. But let's see, what does that mean? That means that length PC over length PO is going to be the same thing as length CD over length OR. So let's write that down. So PC over PO will be equal to CD over OR. But some of those are fairly simple to calculate. Notice it'll be the y-coordinate of C minus the y-coordinate of P because they have the same x-coordinate, but that'll just cancel the minus 1. So that means we have 1 over square root of t squared plus 1 over, well, PO is also easy. That's simply equal to 1. So that's going to be equal to CD, so CD over OR, but the length of OR is T. Okay, but putting this together, that means that C times D is equal to T over T squared plus 1. But then we'll have the area of region B2, which is the same thing as the area of this triangle PCD. Well, that's going to be 1/2 base times height, but that'll be 1/2. The base is CD, which is T times, I missed a square root of T squared plus 1 before, times, well, like I said, our height, which was calculated over here, is 1 over the square root of T squared plus 1. So that makes this T over 2T squared plus 2 after multiplying it out. So let's collect that over here. Oh, but observe that's exactly what we have for the area of A2. So let's just write this is equal to the area of B2. Okay, nice. So now let's see where we can take this. Okay, so motivated by our picture, we just showed the equality of all of these different areas. So now we're ready to make our final calculation. So let's start over here on the left-hand side of the equation. So we've got 1/2 our integral from 0 to t of 1 over x squared plus 1 dx. So let's observe that that's going to be equal to the area of A1 plus the area of A2. And well, that's simply because that integral is representing, well, the area of the sum of the area of each of those. But area of A2 is area of B2. Area of A1 is area of B1. So this makes this the same thing as the area of B1 plus the area of B2. But now the trick here is to calculate the area of B1 plus the area of B2 a different way. So notice this is the area of a sector of a circle with radius equal to 1 and angle equal to theta. So, well, there's a nice formula for the area of a sector of a circle, and that's 1/2 times the radius squared times the angle. So here we've got 1/2 times the radius squared, but the radius is 1, times the angle, which is theta, but that theta is equal to the inverse tangent, the arc tangent of t. So let's see, we've done it. We started over here with our integral and we ended over here with our inverse tangent function. So this is a nice geometric interpretation of the fact that, well, the antiderivative of 1 over x squared plus 1 is the inverse tangent, or the derivative of the arctangent is 1 over x squared plus 1. And that's a good place to stop.